everybody. It's great to be here with you at Pixel Pioneers in my home city of Bristol, which is a lovely place to be giving a talk. And as Phil said, I'd like to talk about something that often gets overlooked in terms of performance, and that's accessibility. I don't mean in terms of how we write code, but more in terms of conventional browser performance and the things that have to happen to make accessibility work for someone like me who uses a screen reader can have an impact on performance. So before we get any further, let's share a quick definition of web performance, because it can vary a little bit and it can mean different things in different contexts. So for the purposes of today, I'm going to assume that web performance means the objective measurement and the perceived user experience of the time it takes for a website or a page to get loaded in the browser and be available for me or somebody else to get busy and start interacting with. And on that definition, an awful lot of stuff has to happen under the hood by the browser in order to get to that interactive point. It's something known as the critical rendering path, or CRP. And in a nutshell, it's the bit that takes your code, your JavaScript, your HTML, your CSS, and converts it into something you can poke, prod, tap, click, and otherwise interact with. But it's a sequence of steps that entails a surprising amount of activity. The first thing that happens is your HTML gets passed by the browser and it creates the document object model, or the DOM. If there's JavaScript being called in your HTML, that too gets recognized and passed, and if it has an impact on the DOM gets refactored. Once all the content of your document is essentially captured in that DOM tree, the next sequence takes place, and that's where all your CSS code gets passed into something called the CSS object model. Now, at this point, you've got two separate structures, your content, which is in your DOM, and all your styles, which are in your CSS OM, but they're entirely separate. So the third step in the sequence is to bring the two together in the render tree. And essentially what the browser does is it walks through the part of the DOM that will be representative of the visual things that you will see in your web page. And as it walks through, it pulls the information out of the CSS object model and maps the two together. So you end up now with a combined content and styles structure. It then moves on to almost the last part in the sequence, which is layout, how essentially everything is going to arrange itself on screen: height, width, proportional representation, representation in relation to other objects on screen, and so forth. And then finally, we get to the last step in the sequence, which is the bit where everything gets revealed on screen so that we can start interacting with it. This step's known as paint. It's when essentially all the pixels get painted on your screen. So clearly there's already a lot going on in the browser to get the web page in front of you to be able to start using. But what happens if you don't look at pixels? What happens if you listen to content on screen instead of look at it? So the screenshot of my blog homepage that's on screen now has been painted pixel-wise, but for me, I need it to be converted into speech, a bit like this.
Heading Level 1, Latest Posts, Article, Heading Level 2, Link, Thoughts on Skin Tone and Text Descriptions, December 15, 2021, List of 1 items, Web Life, List End, Article, Heading Level 2, Link, Patrick H. Law.
So lots of information in there, much of which you're able to see in the pixel-painted version: headings, links, list items, and other bits and pieces. But there's a step that's missing, because obviously paint isn't the bit that's doing that conversion to the synthetic speech. The answer is that the browser is actually doing a little bit more when it recognizes that something like a screen reader is available. It's creating another structure, this one called the accessibility tree. And it's, in some ways, a parallel structure to the DOM. It's all about the content, but instead of having all the information that you'd expect in the DOM, it has all the accessibility information about what's in the DOM. And that accessibility information essentially comes from the HTML, good 95% of it anyway. And that's because most HTML elements have implicit accessibility semantics. In other words, they come with a bunch of accessibility information built in for free. And this is what gets represented in the accessibility tree. So I'll give you a quick guided tour of what that can mean. One bit of information is the element's role, so what its purpose is. And more often than not, this is pretty evident from the element, the tag name itself. So if we take a button, for example, it's pretty clear that its role is button. What my screen reader will do is ask the browser for the information that's in the accessibility tree about this element, and that's what I will get to hear back as a user. So if we see this very simple button element on screen, nothing in it, nothing complicated, my screen reader will tell me that it is
button.
Nice and simple, but it's how I know what I'm dealing with in the same way you probably recognize the button from its visual characteristics. Next piece of information that's commonly found in the accessibility tree is an element's accessible name. In the case of a button, link, other things like this, it most often comes from the text or the content inside the element. So again, if we build out our button example and we add some text inside, let's call it a show password button, screen reader goes to the browser and grabs 2 bits of information, the role and the name, and I get to hear now.
Show password button.
Brilliant. So 2 bits of information tell me not only what it is, but also why it's there. A third piece of information is an element's state, or indeed other properties that describe the current condition that the element happens to be in at the time. So buttons don't really have attributes natively in HTML that change their state so much, but we can use ARIA, accessible rich internet applications, specifically in this case the aria-pressed attribute, to indicate that a button has a pressed or not pressed state. And again, visually this would be represented, of course, by changing the appearance of the button. But again, my screen reader now gets a third bit of information to wrap into the bundle I get to hear about.
Show password toggle button pressed.
So now I know it's a toggle button, i.e. one that can be turned on or off, that it's currently pressed, and therefore, presumably, that my password is currently shown. So all this information gets presented to assistive technologies by the browser through this other structure called the accessibility tree. So what impact does that have on performance? Well, this is a little bit of an extreme example, but I want to show you how it can have an impact, particularly on a page that's got an awful big amount of things in the DOM.
Enter.
Almost.
6 regions, 354 headings, and 6,095 links.
6,095 links ought to be a warning sign, really, when you're building anything, didn't it? But I said this was an extreme, example, but the DOM on this page is humongous, and so the accessibility tree is humongous because the two are pretty much parallel. I think Bianca mentioned, people get fed up and leave pages after 3 seconds. That's closer to 11, which is, astonishing. It is an extreme example. I don't want to give you the impression that all screen reader users are hanging around waiting for decades at a time for pages to load. It's not often like that, but it does have an impact on performance. It's not just the size of the DOM, though, and the corresponding accessibility tree that has an impact. There's also a factor in terms of how the screen readers are getting at the information from the browser. They do this through platform accessibility APIs. There's one, or at least one, on every platform. Windows has 2 or 3, in fact. These are not JavaScript APIs in the ways developers amongst you might well be familiar with APIs. They are just platform level, so they're available to applications and OS level, application level things. But essentially, the screen readers use these APIs to query the browser for information that's in the accessibility tree. To understand the impact this has, we need to just take a little bit of a look in very simplified terms at how browser architecture used to be and how it is now. Back in the day, going back to the 90s, even early 2000s, browsers used to have a single process, which is to say everything, the application, the bits you clicked on, the menus that you looked at for the actual application itself, all of the content, the whole 9 yards, was all in a single process. This was good in some ways. It meant that everything was pretty prompt and pretty available to you. It was also terrible in other ways, highly insecure, somewhat unstable, and so browsers switched, I think Chrome was the first to really start doing this, to a multi-process model, which is now what all browsers do, which is to say there are processes for all sorts of things, many, many different processes. The 2 I want to focus on for now are the application process, so the Chrome, the framework, the menus, and the kind of the outside bits of the browser as you see it on screen, and the content process, the bit that sits inside your tab window. And of course, there might be multiple content processes. These are the two I want to focus on because they're the two that are most important in terms of performance. It's the content process where the critical rendering path happens, and therefore it's the content process where the accessibility tree gets built as well. Another factor is the way screen readers are able to communicate with the browser. Some do it through in-process communication, which is to say the screen reader can inject itself inside the application process and let the application process communicate with the content process. In other scenarios, it's out of process. The screen reader isn't allowed anywhere near the browser processes at all. It's completely ring-fenced. And so any communication happens between the screen reader and the application process and the application process and the content process. So those are the two models that we see now happening in terms of communication architectures within a multi-process browser. I'm going to take you back a little bit to Internet Explorer. Thankfully, not one we have to worry about too much these days, and that's good for all sorts of reasons, not just developmental ones. In accessibility terms, it lagged for a long time. But the reason I want to mention it is because its architecture was a little bit strange. It was still a lot more permissive than we really believe is sensible these days. The screen reader existed or injected itself inside the application process, but it had direct access to the content process. So this had both good and bad effects. On the one hand, performance was actually really good because the screen reader had direct access to the accessibility tree. It could grab all the information it wanted about whatever was on screen, names, roles, states, the whole 9 yards. So it was very, very performant in terms of accessibility performance. The problem was that it was highly unstable. So if the browser crashed, it took out your screen reader too, which is kind of the equivalent of a blue screen of death for those of you who happen to remember such things. Without a screen reader running, a blind person is pretty much fundamentally unable to do anything. Because of the way screen readers were at the time, it often meant you had to reboot your whole system in order to restore things back to normal. So great performance right up until there was no performance at all. So things have moved on, thankfully. We can look at Chrome and Firefox for examples of how this stuff works today. They both use in-process communication architectures, but they've got that sandboxing in place. So the screen readers inject themselves into the application process, but cannot touch the content process at all. All that communication happens by the browser between the application process and the content process. So remember, we've got the accessibility tree in the content process, and here we get down to the different ways that the API calls can be made. Chrome, when they first started doing this, took an interesting approach. They insisted that the screen reader could make a query using the accessibility APIs. It would send that to the application process would send it to the content process would get the information out of the accessibility tree, send it back to the application process, which would give it to the screen reader, one bit of information at a time. It's not rocket surgery to figure out. That was going to take a while, whichever way you looked at it. Fortunately, the people at Google figured out there was a better way to do it, and what they switched to and what they still do now is that they actually cache the entire accessibility tree. They copy it from the content process where it's created and then dump the entire thing in the application process where the screen reader can get its mitts on it really, really quickly. So sometimes there is a bit of an initial hit while the accessibility tree is built and then cached across to the application process. But after that, things are pretty much lightning fast. And that video I just played earlier is, as I said, extreme example of that initial hit. But that page, once you've got your 6,930 million links loaded up, and God knows what else was there, actually is very, very responsive. It's a highly performant experience in Chromium browsers. So that's the current model there, and it's working pretty well, all things told. This means, yeah, Firefox performance, Chrome performance, you've got possible hit on the initial TTI, but after that, yeah, things are pretty positive in terms of performance. Firefox takes a slightly different approach. It borrows a bit from Chrome's original approach. It proxies all the API calls from the application process to the content process, but it uses something it calls intelligent caching, which is to say, when it gets an API call that wants something like some text content from the accessibility tree, an accessible name, for example, it will try and intelligently guess what other information, what other properties the screen reader might also want to know, and it'll bundle it up and send it back with the response. So you might get information about whether the text is bold, for example, or other properties about the text. This means it works reasonably well. Performance is okay, both in terms of time to interaction and subsequent performance, but okay is, yeah, kind of could be better. And I love Firefox, it's my preferred browser, but sometimes it does just feel a little bit sluggish, or what's the phrase I learned while I was looking some of this stuff up? Janky, bit sluggish, there we go. It's a terrible word, whoever came up with that. But it's true, things just don't feel quite as slick and efficient as you want them to be. The good news is, imminently, as in sometime in the next month or so, Firefox is going to switch to using Chrome's model. It's going to start caching the entire accessibility tree within the application process. I understand from the accessibility team at Mozilla, this is going to land behind the flag sometime in the next month. It should be rolled out, assuming everything goes okay, to all users in a shipping version within the next 6 months, I understand. And that's going to be a really big step forward at the moment, because it has to be said, right now, and this is particularly since Firefox went through the switch to Quantum and such, its performance hasn't been as good as Chrome's and the other Chromium browsers. So this is a really welcome kind of move from Mozilla, from my point of view as a screen reader user. Safari is a little bit different. It actually uses the out-of-process communication architecture. So this is where the screen reader gets nowhere near the browser at all. And you might think that this is a real hit in terms of performance, but oddly, it's not. The reason is that on both iOS and macOS, there is only one screen reader, and it's provided by Apple. And so, like many things that are built within the same ecosystem, they work extraordinarily well together. So actually, the performance for using the voice-over screen reader with Safari browser is remarkably good. It's very, very efficient. The performance feels very clean and efficient, and it's really, really good. This, for those of you who are curious in looking back a little bit, is exactly how it used to be in Edge on Windows before Edge switched over to using Chromium. Before that, used with Windows' own integrated screen reader, Narrator, the performance was absolutely excellent. But if you used either of the other installable screen readers on Windows, JAWS or NVDA, we saw very, very sluggish returns. And that was because the out-of-process architecture, coupled with some more constraints about sandboxing, the way the API calls could be made the whole process really sluggish. So again, much as I was sad that Microsoft gave up working on its own rendering engine, from an accessibility performance point of view, it made strides ahead in Edge. So we've got our accessibility rendering path, which is essentially the same. We've got the DOM, the CSS object model, we've got the render tree, then we've got the layout, and then we've got an accessibility tree. Well, almost. Of course, paint still happens, because most of the rest of you would be pretty miffed if stuff didn't start appearing on your screen. Although part of me thinks, welcome to my world. I've spent so long not being able to access stuff, maybe a little bit of, but no, that's just terrible of me. So we've got all this stuff going on in the browser, and you might think that that's all there is with regards to performance. There's one more thing, though, and that is particular to Windows screen readers, and it's known as the virtual buffer. The virtual buffer is as its name suggests, it's a sort of virtual version of the page that the screen reader creates for itself. All of the information comes from the browser, so I don't want to give you the idea that the screen reader is just going off and passing HTML or any of that stuff for its own. They used to, back in the sort of original days I was talking about with the single process model, but this is just a virtual recreation of the DOM, the accessibility tree, and all that information. And you might ask yourself, well, why bother? Surely everything we need is in the browser, in the accessibility tree, the DOM, and all the rest of it. The answer is yes, it is, but there's a bit of functionality that most screen reader users would really miss if it wasn't available. And that's the ability to navigate around content in ways that are a lot easier when you can't see the content. As a sighted person, you'll get used to spotting the thing you're interested in on the page, clicking on it, moving to it, scrolling to it. You hone in, you target, you acquire your target. With screen reading, you can't do that. You have to just navigate through things. So, for example, the virtual buffer is what gives us the ability to, instead of listening to the whole page, like I showed you right back at the beginning of the talk, to jump, for example, just between headings.
Latest posts, heading level 1. Thoughts on skin tone and text descriptions, heading level 2, link. Patrick H. Locke's Goulash, heading level 2, link. Notes on synthetic speech, heading level 2, link.
So it gives us very quick ways of being able to navigate around. It also gives us other useful features. We can bookmark certain points on a page, so we can just return to a very specific spot in a document just at a key press. does even better things. We can get it to ignore iframes that look like advertising, so we can just vanish them out of our eyesight entirely, as it were. So this is the reason why, for the time being, the virtual DOM is still a very useful thing. So in terms of improving accessibility performance, that's often a thing that gets suggested, but it's still a remarkably difficult thing to do until things like the APIs, the accessibility APIs, improve the way that they are able to share information or query information. And that's a huge undertaking. So at the start, in the definition of web performance, I mentioned two things. One of them was perceived experience. And here, it's remarkable how much tiny little things matter. For example, a change that recently is coming along in Firefox is that they're changing the order in which that they process events. They're going to put the focus events processed first, and then after that, they'll process any other change events that come along, whether that's properties or other styles or anything else that comes along. And the reason is that even though we're talking about milliseconds, probably single-digit milliseconds, focus is the first thing that a screen reader needs to know has happened, because at that point it can start reading the content from the point of focus, and everything else can kind of slot in behind it. And it makes a remarkable difference to your perceived experience. In objective measurements, sure, we could measure it, but it's a tiny, infinitesimal amount of time. But when you're banging through a page and you just want to navigate, you want to get somewhere, you want to focus on a link, you want to know what the link is, you want to hit it, go for it, move, these things really do matter. Little changes matter. In terms of objective measurements, this one's interesting. There's been a conversation going on the Google Lighthouse repo for a couple of years now, due to a conversation that I had with others on Twitter, asking for a metric that will enable us to, in some way, shape or form, measure time to interactive if you happen to have an assistive technology like a screen reader running. It might be time to first API call on the accessibility tree. It might be actual time to first interactive measured in some ways. Basically, I think it needs someone who's got knowledge of how things like Lighthouse works to be able to put some demos and examples together, which sadly is way beyond my scope of experience and capability. But if you're interested in joining the conversation, the issue link is on screen, and you'll find it by heading to the Lighthouse and searching for metrics for inclusive, for assistive technologies. But it'd be great if anybody's interested in this area to get more thoughts and ideas and suggestions on how this might be realized. And finally, some practical steps. What can you do to improve accessibility performance? Well, the short answer is nothing that you shouldn't already be doing to improve performance anyway. If you haven't really given it much thought up until now, two things I would recommend. MDN has some really excellent articles on performance, critical rendering path, all sorts of other things, how to use features like lazy load, web workers, all sorts of things that can help you get your startup time and your performance metrics in much better shape. The other thing is to use Lighthouse for its existing performance metrics, because the more you can do to make your website performant to begin with, the more you're going to do to make it accessibility performant too. It is very much part of the same ecosystem. So yeah, take a bit of time to learn about it, and keep your DOM size small, whatever you do, please. Keep your download size file size is small, all the stuff you probably know about, because whatever impact it has on most people's performance, it has even more of an impact on the performance for screen reader users. And I hope that's given you a brief tour of accessibility performance in browsers. And I hope next time it won't be something that I think Time to Interactive forgot. Thank you.